Solution stoichiometry. So essentially what this is just using your problem solving skills developed during normal reaction stoichiometry and applying that specifically to questions involving solutions. So let's go through a couple of examples here. Here's a fairly general solution stoichiometry question. It's asking what the volume of a 2 molar, so this is again moles per liter is what that capital M means. So a solution that is 2.00 moles per liter hydrochloric acid. So what volume of that solution does it take to completely react with 24.31 grams of magnesium metal? So to start off, we'd want to write the reaction for this. So magnesium plus HCl, we're going to form hydrogen gas and magnesium chloride, and we're going to make sure that equation is balanced. So we have our equation to base our stoichiometry calculations on, and we're going to start with the number given in the question, 24.31 grams of magnesium. So we're starting off with that much magnesium, and we want to know how much HCl is required to react with all of that magnesium. Just like before, we're going to take our mass, we're going to convert to moles so that we can apply the 1:2 ratio over, and we can find out how much HCl it would take to react with it. But the difference here is it is asking for volume. It's not asking for mass, it's asking for the volume of HCl. This is a solution. So at some point, we'll have to turn our answer from moles into a volume. So first, let's go to moles. So take 24.31 grams of magnesium, use the molar mass, and we will have the moles of magnesium. So we have 1 mole of magnesium we're working with. We can then find out how much HCl it would take to react with that by using the mole ratio. So I'm going to rewrite that 1 mole of magnesium, and that should actually be 1.000 to have in proper signifiers. And we have our mole ratio of 1 mole of magnesium to 2 moles of HCl. So moles of magnesium cancel out, and we are now talking about moles of HCl. That's how much HCl is needed to react with the magnesium. But the question is not asking for moles, it's asking for volume. So we can take this one of two ways. We can take this and we can say, okay, well, I know my concentration equation. The concentration of a solution is equal to the number of moles over the volume of the solution. We have the number of moles here. Also given to us, let's go back to the question, is the concentration. So with our equation, we can rearrange it to solve for what the question is asking for volume. We can take our number of moles and put it in for N. We can take our concentration from the question, and we have 2 moles of HCl, and the concentration is 2.00 moles per liter. So that would give us a volume of 1 liter. It would take 1 liter of this HCl to react with the 24.31 grams of magnesium. Quicker way of doing that, as all questions should be done, is with conversion factor. Exact same math, we're just going to skip the process of writing out the answer in between each step and just apply these conversion factors one after another. And what you'll find is you're not going to have to worry about sigdigs. You're not going to worry about rewriting the numbers and making transcribing errors. Also, you're not going to worry about equations, memorize equations, rearrange equations, if you use conversion factors. So the first one gets us 2 moles of magnesium. The second one gets us 2 moles of HCl. Same calculation we did before, we're just doing it all at once. The third one here, so let's go through the math here. We've got grams of magnesium canceled out with the first conversion factor. Moles of magnesium is canceled out with the second one. And now we're in moles of HCl. That's the unit we're looking at right now. So if we cancel out moles by putting moles in the denominator here, and we have liters up top, our answer will be in liters, which is what we're looking for. We're looking for the volume. So this conversion factor here is the concentration. Because remember, concentration is just an expression of how many moles there are per liter. So I'm just writing it, and I'm saying 1 liter has 2 moles in it for this particular acid. And I'm putting moles in the bottom so that it'll cancel out. And I'm putting liters up top because that's the unit I want to carry through to the end. So I'm using conversion factors. I'm doing the exact same calculations, but I can do it all in one step, avoiding copying errors, avoiding worrying about sigdigs and rounding and all that, and I get the exact same answer much quicker. Alright, let's try another one. This one is looking at concentration of ions. So let's say we have some NaCl. We put 12.6 grams of it into 250 milliliters of water. what is the concentration of the sodium ions in that water. So first off, again, when we're talking concentration, let's as otherwise assume we're talking molar concentration. So we need to have moles and we need to have liters to get to our answer. Right now we're in grams and we're in milliliters. So we just need to convert grams to moles, milliliters to liters, and make sure the moles is over the liters, and we will be in molar concentration. So starting off with the mass of the sodium chloride, I want to go to moles using my conversion factor to get me to moles of sodium chloride. Now for the sodium ion, it comes from the sodium chloride, and it's a 1 to 1 to 1 ratio for sodium chloride to sodium ions to chloride ions. So I should take this number and run it through my 1-to-1 conversion factor, which is not mathematically very difficult, but I would end up with obviously the exact same number, but now I'm in moles of sodium. Don't forget this step here, because if it's not a 1-to-1 ratio, it will matter if you forget to do it. Then I want to go to concentration. I have my moles, I have my volume, so I can plug those in. There's my moles there. My volume I've converted to liters, and I get a concentration of my sodium ions in moles per liter. Also, we can do this quickly, set up the exact same calculations, avoid worrying about the formula just by working the conversion factors and working the units. So, first conversion factor, just like above, convert to moles. That's mole of sodium chloride. I should convert that to moles of sodium, and yes, it is a 1-to-1 ratio. Now, mass is gone. Moles of sodium chloride are gone, and now I'm in moles of sodium, and I want my answer to be in moles of sodium per liter. So I already have moles as a numerator. That's where I want it to stay. I don't want to divide by it. So my next conversion factor, let's see, it ends up there. I don't want to get rid of moles, but I do need to have, because this is concentration, I do need to have liters on the bottom. So what I'll do is I'll use the volume I'm working with, which is here written in liters. I'm going to use it as a denominator. Same thing as dividing by 0.250 liters. I'm just keeping it in the same format by writing it as multiplied 1 over 2.5. Moles will carry through to the end because nothing canceled it out. Liters will carry through to the end because nothing canceled it out. And I will have my answer in moles per liter. So I'm using the volume itself in the given situation as a conversion factor just to get liters as a denominator on the bottom. Alright, let's try one with a percentage calculation in there as well. So you're told a banana has 0.61 grams of potassium phosphate in it. It's a 250 gram banana, and you want to find out what percent by mass of potassium is in the banana. So we're going to have to take this grams of potassium phosphate, convert it to moles of just potassium, moles, and then just to potassium, which we're going to have to turn into mass because it's a mass percentage here. And we have our mass of banana we'll use at the very end. So let's start off with the number we have, and in order to convert from potassium phosphate into potassium, we're going to have to know that ratio in moles. The potassium phosphate has 3 ions of potassium for every 1 ion of phosphate in there. So if I have a mass of potassium phosphate, I can't just multiply it by 3 because it's not a, this is a 1 to 3 ratio, not in mass but in moles. So like most calculations in chemistry, we're going to have to convert into moles first. And so use the molar mass of potassium phosphate to 12.27, and that will give me my moles of potassium phosphate. Now I can convert to moles of potassium. So it's a 3-to-1 ratio. So I'm basically multiplying the moles of potassium phosphate by 3, and I get my moles of potassium ions. Now, this is a mass percentage calculation, so I can't use this. I'm not doing a moles per liter calculation. I'm doing a mass percentage calculation. So I'm going to have to take my moles of potassium now and convert them into grams. So moles of potassium will cancel out, and my answer will be in grams of potassium ions. Now, molar mass of potassium ions, I'm using the same molar mass of potassium. Yes, it has 1 less electron. That's not going to factor into the mass at all. This is the mass of potassium. 250 is the mass of banana. So if I want to know what is the percent of potassium in this 250 gram banana, I would take the portion and divide by the whole, and I want to express it as a percentage, so I can multiply that by 100, and I get 1.3% potassium in the banana. Quickly, conversion factors, we can do the first 3 steps just like we did when we did mass to mass stoichiometry. So we're taking our grams of potassium and converting it into moles of potassium phosphate. I don't know what that is. Moles is then converted, potassium phosphate is converted to moles of potassium, which is then converted into mass of potassium, and we'd get our 0.337 grams of potassium. Divide that by, that's the portion that we are dividing by the whole mass of the banana, and that would equal, if we wanted to write as a percentage, multiply by 100, and you get your 1.3%.